In the notes, our what we've been calling H sub D, has been a 3 by 3. So in our entire example so far, it's been that 3 by 3 matrix in the notes. And now, so you can do something without having to worry about a matrix, it's 1 by 1. It's your device Hamiltonian, what we've been calling H sub D, is what? What is your device Hamiltonian? What is H sub D in this model? From equation 1.178 there, what is H sub D? Okay, well, there's only 2 matrix elements shown, so you got a 50% chance of getting it right. What is H sub D? Epsilon, there you go. That's H sub D, epsilon. It's just a number, the site energy of site 1. That's your H sub D. Okay? And then, what do we want to do? So, H sub D is epsilon, okay? Starting from this relation, and now H sub D is just a number, epsilon. Derive an analytical expression for the green function of the, quote, device, which is, just site 1, 1. So the green function of the device is just G11. Okay? We just want to calculate G11, and we're going to do it by, so let's see, do I have any examples? So we're going to follow exactly what is done in the notes and in this chapter preceding it. In a 1 by 1 matrix, let's go back and look at our example from a 3 by 3. 3 by 3, where is it? Here it is. So, right now, in our 3 by 3 example, this site 1 couples to the left lead, this site couples to the right lead. But now we only have this site. This is the only site, and it couples to both the left and the right lead, which means this simply becomes E minus epsilon plus this, since it's coupling to both leads. So the self-energies from both leads get added onto the central site. And that's it. And well, that's going to be the inverse of your green function. So E minus epsilon plus this, and now the k's are the same since it's just a uniform chain. So K left equals KR, right equals K. That is the green function of site 1, 1. And so, where are these? Here. And so you just, you have E minus epsilon minus those 2 self-energies, or it'll be plus magnitude T e to the I, plus, in this case, 2 magnitude T e to the I Ka. Inverse, the whole thing inverse. And so you take the inverse and you derive these expressions for G as a function of K, velocity, and energy. And you're going to be using the tight binding dispersion relationship to do that, because you're going to have, an E minus epsilon minus 2T e to the I Ka, and you're going to be able to manipulate things in terms of, that EK relationship is E equals what? Epsilon plus 2T cosine Ka, and so you can, and to get the velocity, that's the derivative, 1 over h bar d e dk gives you velocity, and that was, related to sine Ka. So using those relations that you get from the tight binding dispersion relationship relating E to K and velocity to K, you can write this in 3 different ways. So that's what you do. And in this case, as I note, since every site is identical, this will be the exact green function for any site in this chain. Right? There's no difference between one site and any other site. We just arbitrarily called site 1 the device. But all sites are equivalent. We could call any other site the device. So this is a diagonal green function for this ideal 1D tight binding crystal. Okay, and then, well, this is trivia. Once you have the green function, you're just going to write down the spectral function in terms of K, V, and E. It's pretty trivial once you've already done that for the green function. The spectral function is just -2 imaginary G. But just to gain, it's mostly for you to gain some insight into the relationship between the green function and the spectral function and the velocity in K. Because I think, I mean, I can't remember whether it's like 1 over velocity or velocity. I can't remember right in the moment. Okay, and then, so then I say, show that the spectral function, prove that, we said that it's true, and now I'm saying prove it, that the spectral function is equal to 2 pi a times the density of states of the 1D chain that you get from this dispersion relationship that we calculated in 208 last quarter. So we calculated in the early part of the course, and it's probably in the PDF notes and somewhere in your notes, the density of states from this 1D tight binding model, like the first several weeks of the course. So, and also the PDF notes are uploaded, so it's in there also from 208. And I think the PDF notes are also on the EE212 website. So the PDF notes for 208 are also under course materials for 212. So you can, if you can't derive the density of states from this, then you can find the expression in the notes. And then prove this by just explicitly. You're going to have an expression for the spectral function in terms of energy, and prove that if you integrate over energy, it's equal to 1. So physically, what does that mean? That this integral is equal to 1. I mean, what is the meaning of the spectral function? What is the meaning of the density of states? And well, okay, no one's going to venture a guess here. So last time we defined what we call G sub n and G sub p, where G sub n gives you like the we call it the electron density. And just think of one band, which is all we have. And G sub p gives you the whole density, which is the absence of an electron. So if you're looking at a single site, if you sum up, the sum of the two is the sum of what you call the empty states plus the filled states would be all the states, and that was the spectral function. The spectral function, like the density of states for a given site, would be the total number of states that you have on that site if you integrate over all energy. So this is just saying that you have one state per site, and that is our basis, right? That's what was our starting point. We have one s orbital per site, and that's just telling you that it's normalized, that there's one state per site, which was our starting point. So if we had an sp3 basis, then you would, then you would have this an a for each an a for each orbital, and if you sum up over all the orbitals on a single atom, you'll just get the number of orbitals if you integrate over all energy. But we just have one orbital per atom, so this is going to give you 1. So I just have you explicitly show that later, much later, when we redo everything from second quantized point of view, you're going to see the spectral function is given by this quantity down here, where these are your electron creation and annihilation operators for, say, site N. And I don't know if you've come into contact much with these, but if you look at this is just an anti-commutation right here. And the anti-commutation of two fermion operators like this is just going to give you 1. Right? That's the anti-commutation of C dagger C, or C dagger and C. And so by definition for any Fermi operators, that's going to give you 1. We'll see later that this is another definition of that. We're going to redo everything, hopefully, from second quantized point of view much later. And from this, it's obvious that this must be equal to 1. A trained monkey could see this. Anyhow, so let's see. Number 5. Using the one node, show the transmission. Okay, so for energy within the band, you go ahead and go ahead and calculate the transmission, and then you show that for any energy that's within the band of the structure, that the transmission coefficient is going to be 1.0. Because it's just an ideal crystal. There's nothing that's going to give you any reflection. You're injecting from a lead through the device into the next lead, and it's all complete. There's no change in potential anywhere. It's just an ideal periodic crystal. So whenever that's the case, your transmission is just going to be 1.0 for any propagating state. So you calculate the transmission using the expression. So you have, at this point, you have your G11, right? Your exact G11. And so then you go back and you find the expression for transmission. And you have your sigmas. You have your sigma left and sigma right. They're the same as always, right? And you've got your gammas related to your sigmas. Right? You know your gamma left and gamma right. It's -2 imaginary of your sigmas. Right? So it's -2 imaginary of this thing up here. Right? Those are your gammas. So you have your gammas, you have your green function, and that's all you need to get the transmission coefficient. Okay? So you multiply that out, play with it, and show that everywhere within the band is equal to 1.0.
You said you read it out like this because later at some point each one of those...
Yeah, for now there's all a scalar, so it'll be gamma squared magnitude of G squared, right? Like, did we first write it like that somewhere? It'll look, right, like, it'll just be G11 squared gamma squared, because the gammas are identical, and G is just a scalar. So it'll be magnitude of G squared gamma squared. And so next Monday I'll be traveling, so there'll be no class on Monday. Be back on Friday. So does that seem clear? That was that's it. It was 1 through 5. And I mean, once you have the exact green function, everything else is just. And to get the green function, you need the sigmas. So you have the sigma, you have the green function. From the sigmas, you have the gammas, and so you have everything you need.